Alright, so today we're going to be talking about the Time Domain Reflectometer, or otherwise known as the TDR. So to begin, let's start by drawing a TDR. So what we have is a voltage source, VG, which is a DC source, connected to an impedance of ZG, which is then connected to a switch. Across here, we will have a voltmeter, and all of this will be connected to a transmission line of some characteristic impedance Z0. So what we have on the left over here, this is our TDR. So now what does a TDR do? So to explain that, or how does it work? To explain that, let's look at a simple example. So let's say that transmission line over there is of length 10 meters. And let's say this load is open circuit. So we're going to connect our TDR to this transmission line and see what happens. So how the TDR works is using this switch. It's going to flick very fast, and that will create voltage pulses, which will be sent out by the TDR. These voltage signals will will propagate down the transmission line, and once they reach the load, depending on its reflection coefficient, they might or might not cause a reflected wave to come back. And all of this will be logged on the voltage at the TDR will be logged by a voltmeter over time. So let's take a look at what the TDR sees in this example. So if we plot the voltage versus the time, so initially we'll get a forward propagating wave from the TDR. Then once it reaches the end, if it takes time t to reach the end for the wave to propagate down the transmission line, it'll take time 2t for it to come back. And then once it comes back, since it's an open circuit, the reflected wave will be 1. So the final voltage will be times 2 the initial voltage. So why is this important? Well, if we have both the voltage and the time, then if we give the TDR the velocity, then since the TDR has the time, we are able to get the distance. And now this is the most important part of the TDR, because now the TDR can tell us that this open circuit happened at exactly 10 meters. So this is really crucial because the TDR's most common use is to test the validity of cables. Because, for example, say that this 10-meter cable actually had a short at 4 meters. Then our TDR would be able to tell that, because we'd see a sort of, the TDR would show us a graph where at distance 4 meters, we'd have a short circuit. So we've already discussed that a TDR could be used to measure and check the validity of cables, but if we scale that up to industry, a common example of where a TDR is used is on airplanes. So if you consider the amount of wiring an airplane has, it can literally have miles and miles of wiring. So if there was a fault in any of those wires, if you wanted to find that manually by searching the airplane, that simply wouldn't be feasible given the volume of wires and also the feasibility of trying to dismantle the airplane and search for it. By using a TDR, we could measure the exact place that fault is at, and say if it was here, we'd be able to pinpoint that location, that, oh, it's exactly right there, and we can just go in and directly fix it. So now let's take a look at a couple of examples. For the following examples, we will look at the setup we have below. So what we have here is we have on the left side, we have our TDR. And our TDR will have voltage VG, impedance ZG, and it'll be connected to a transmission line of characteristic impedance Z0, which will then be connected to some load. And what we're going to do is we're going to examine what the TDR will see as the voltage versus the time to gain an intuition to understand how a TDR will work with different loads. So let's take a look at our first example, and let's say that our load will be some impedance of Z1, and that Z1 will be equal to 1/3 Z0. So what's going to happen here is that since ZG and Z0 are matched, the initial wave that will propagate down the transmission line will be a voltage divider between a VG between ZG and Z0. So that's going to be 1/2 Vg that will initially propagate down the line. So if it takes time t to propagate down the line, then at time 2t, the reflected wave will return to the TDR. And now the reflected wave will be new minus old over old minus new. So 1/3 minus 1 over 1/3 plus 1 will be equal to 1 minus 1/2. So what that means is because z1 is 1/3 of z0, we're gonna get a reflected wave that is minus 1/2 of the forward going wave. So minus 1/2 of 1/2 Vg will be minus 1/4 Vg. So that's the wave. So this wave right here will be minus 1/4 Vg, which will propagate back down the line. And if it took time t to reach one end, it takes time 2t to reach back to the TDR. And then once that hits the TDR, the voltmeter will register a drop in voltage of minus 1/4. So we'll end up with the final voltage being 1/4 Vg for the rest of time because there will be no more reflections. All right, now let's take a look at a second example. For our second example, we'll have the same setup as we did for the first example, where Zg and 0 are again matched. So now we're going to connect a capacitor for the load instead of a resistor. So again, similar to the last example, our initial forward propagating wave will be Vg by 2. That will propagate down the line, and once it hits the end, it'll see the capacitor. Now, if you remember, what happens with a capacitor is that it'll resist a change in voltage. So the initial reflection coefficient will be -1 because it'll be a short circuit. So that -1 will propagate back down, and at time 2t, we will see a short circuit. However, as that capacitor charges up, that short circuit will eventually become an open circuit over time. So eventually, the coefficient will slowly rise, and it'll eventually become an open circuit, which has reflection coefficient of 1. So then we will have Vg as our final voltage over time. For our third example, we will again have the same setup as our previous two examples, except now instead of a capacitor at the load, we will have an inductor at the load. So similar to our previous two examples, because because Zg and Z0 are matched, the voltage coming out of the TDR will be the voltage divider of Vg over two equal resistances, so it'll be Vg by 2. This voltage will then come out of the TDR and propagate down the transmission line, and eventually it'll see the inductor. Once it sees the inductor will initially act as an open circuit because an inductor opposes a change in current. So this means initially the reflection coefficient will be 1, and that means that all that Vg by 2 all the voltage will be reflected back down the transmission line. And at time 2t, the TDR will see that the voltage will be Vg because Vg by 2 plus Vg by 2 is Vg. And then as time goes on, the inductor will begin to charge. And as the inductor charges, it'll slowly become a short circuit. And a short circuit as t goes to infinity. And a short circuit has a reflection coefficient of -1, so eventually the voltage in the line will be 0. For our final example, we will take a look at something a little bit more complicated. So initially when the TDR is turned on, the voltage that will be sent out by the TDR will be Vg by 2 because Zg and Z0 are matched, and therefore it'll be a voltage divider of two equal impedances. So as this voltage will propagate down the transmission line, and if it takes time t to reach the end of the first transmission line, then we'll have something like the TDR will see something like this initially. Now here's where it gets a little bit tricky. So once the voltage reaches the load, the actual load that the transmission line will see will actually be all of this right here. So what that is the impedance is this impedance in series with the parallel connection of this capacitor and also this transmission line of characteristic impedance Z0. But from a previous example, we know that a capacitor will initially behave as a short circuit. So what that means is initially the load will only be this impedance right here. So that means our initial reflection coefficient will just be minus 1/4. So that means minus 1/4 of the initial wave will be reflected back down. So that means that will be minus Vg by 4. So that means that and if it takes time t to reach the end, it'll take another time t to come back. So at time 2t, we will have voltage Vg by 4. Now, as time goes on, this capacitor will begin to charge up, and as it begins to charge, it'll eventually reach an open circuit. So as time goes on, more and more voltage will be sent down this line, and eventually what you're going to see is that the final impedance will be the series of both the impedance and the characteristic impedance of the transmission line. So that means it's 1.6 Z0, so we're going to have a reflection coefficient about 0.23. So that means eventually the reflected wave will be about 0.23 of Vg by 2. So that means we'll have something a bit greater than Vg by 2. So this is what we see here. As time goes on, the reflection coefficient will slowly increase and we will reach this steady state. Once we're inside of this transmission line here, nothing of importance will happen because this Z0 and these two are matched, so there will be no more reflections.